You are in a dark backyard just after midnight, and the air is so still you can hear your own breathing under the stars. A black hole is our subject tonight, smaller in the sky than your fears would guess, and quieter than any storm. If one ever entered our solar system, it could change the path of planets, the light on Earth, and the way we think about danger in space. And the truth is stranger than the panic. Join this channel now, and each week you get one more piece of the universe explained in a way that actually stays with you. At first, your mind probably does what almost every mind does. It imagines a mouth in space. It imagines the sun yanked away, Earth ripped from its path, and the whole sky folding inward like water down a drain. That picture feels right because black holes have the darkest reputation in science. They do not glow. They do not flash a warning sign. They sit inside our imagination like a perfect trap, a thing that wins simply by being there. But space is not a haunted house, and physics is not a ghost story. The universe does not care what feels dramatic. It only cares about mass, motion, distance, and time. That is why the real answer begins in a colder place than fear. So tonight, we are going to run the simulation slowly. We will watch the outer edge first. We will track what changes, what stays the same, and what happens when a dark object enters a system built on balance. And by the end, the thing that scares you most may not be what you expected at all. Picture the solar system less like a row of planets and more like a moving song. Each world keeps time. Each orbit fits with the others. A black hole does not arrive as a movie villain in that song. It arrives as a new note, and whether the music bends or breaks depends on how heavy that note is and where it enters. To see why this matters, we need to step back. Most people believe a black hole is basically a cosmic vacuum cleaner, a thing that swallows everything around it the instant it gets near. Most people also assume that if one entered our solar system, the story would be short, loud, and final. That is the picture we start with. A dark intruder appears, and everything ends. Hold that thought for a moment, because it is exactly the thought this simulation is about to test. Black holes have been treated like monsters for so long that we forget what they really are. They are not magic. They are not holes punched through space. They are mass packed into a region so small and dense that escape becomes impossible once you cross the boundary called the event horizon. NASA puts it plainly in its Black Hole Basics page. A black hole is not a wormhole, it is not a portal, and it is not a cosmic vacuum cleaner that somehow reaches out and drinks the universe from a distance. That last part matters more than almost anything else in this story. Far away, gravity from a black hole works the same way gravity from any other object of the same mass works. The name changes your feelings. The mass and distance control the outcome. That sounds simple, but simple ideas can take years to feel real. When people hear black hole, they do not picture math. They picture teeth. They picture a trap door in the sky. Part of that comes from how black holes are found. You usually do not see the black hole itself. You see hot gas glowing around it. You see stars whipping around an invisible center. You see light bent by gravity in a way only a huge hidden mass could cause. So the black hole enters the human mind already wearing a mask. It shows up as bent light, torn gas, and strange motion. It becomes easy to think of it as a kind of hunger rather than an object. It becomes easy to forget that it still obeys rules. Even its most famous edge, the event horizon, can fool us. That name sounds like a wall or a shell. It is neither. It is a boundary where getting out stops being possible, not a giant net spread across the solar system. And black holes come in different sizes, which changes the script. Some are only a few times the sun's mass. Some are millions or billions of times the sun's mass. Some scientists even study the idea of tiny primordial black holes, ancient leftovers from the early universe, with masses closer to asteroids or planets. That range matters because the title question sounds singular. What if a black hole entered our solar system? But there is no one-size answer, because a black hole the mass of an asteroid and one the mass of a star do not make the same entrance. They do not leave the same fingerprints. The nearest known black hole NASA lists is Gaia BH1, about 1,500 light-years away. That is not around the corner. It is not even close to close. But the fact that one can sit out there, dark and almost hidden, reminds us that black holes are not just story pieces. They are part of the real neighborhood of the galaxy. Now bring the camera inward. Our solar system is not only the Sun and 8 planets, it also includes belts of rock, drifting dust, wandering comets, and a distant shell of icy bodies called the Oort cloud. It is tidy only if you look from far away. Up close, it is a moving mess held together by rhythm. Mercury races, Jupiter drags and shapes. Comets dive in from deep darkness and then flee again. Tiny objects keep records in their paths, like footprints that gravity leaves in sand. That is why a black hole would not announce itself with a roar. At first, it would announce itself with motion. Something would be slightly off. Some orbit would wobble. Some incoming object would arrive from the wrong place at the wrong speed. This is where the real papers start to matter. In September 2024, Science News reported on 2 teams studying how tiny primordial black holes might betray themselves inside our own solar system. These would not be giant star killers. They could be as small as a hydrogen atom in size, while still carrying enormous mass. Sarah Geller, a cosmologist and National Science Foundation fellow based at the University of California, Santa Cruz, worked on one of those ideas. Her team argued in Physical Review D that a close flyby from a primordial black hole could make Mars wobble in its orbit around the Sun. Not explode, not vanish, wobble. That single word already sounds less dramatic than the movie version, but do not mistake less dramatic for less important. A tiny change in an orbit is like a wrong beat in a song everyone depends on. It tells you something invisible just touched the system. Around the same time, Sebastian Claes and colleagues at the Université Libre de Bruxelles and the Royal Observatory of Belgium explored another clue. A primordial black hole flyby, they argued in another Physical Review D paper from September 2024, could jostle GPS satellites. Again, not vaporize them, jostle them. Think about how strange that is. The first whisper of a black hole in the solar system might not be a torn planet. It might be a small, detectable change in the machines that help your phone tell you where you are. Something cosmic, something domestic. The universe works like that more often than we expect. There are older ideas, too. In 2023, Yuri Eroshenko wrote about the possibility that a captured planet or a primordial black hole in the outer solar system, around roughly 300 to 700 astronomical units from the Sun, could scatter dust inward. That work appeared on Archive and in astronomy reports. Even out there, in the cold edge region, a hidden mass could leave tracks. Then there is the work from Harvard and the Black Hole Initiative. Avi Loeb and Amir Siraj proposed that if a planet-mass black hole sat in the far outer solar system, it might reveal itself through bright flares caused by small Oort cloud objects getting torn up and falling in. That was their central idea. A black hole might be dark, but what it disturbs does not have to be. And yet, when most people hear all this, they still hold on to the older picture. They hear black hole and think only of swallowing. They imagine a dark sphere moving inward and every planet lining up for doom. They imagine that once the intruder crosses some invisible border, the story is over. That is understandable. Black holes do destroy things. Get too close and the outcome is brutal. Matter can be stretched, heated, torn, and trapped. NASA even uses the wonderfully awful word spaghettification for the squeezing and stretching that happen near one. So Act 1 of the fear story writes itself. A black hole enters. Gravity wins. Everything falls in. End of simulation. But that picture is about to change. The black hole is dangerous, yes, but danger in space is often slower, more uneven, and far more dependent on distance than our instincts allow. What we have just taken for granted turns out to be only the loudest version of a much larger story. Write the moment your old picture cracked in the comments. That one line helps us see which ideas deserve the next deep dive. So now the simulation begins for real. Not with Earth, not with the Sun. With a dark mass crossing into the farthest outskirts, where the solar system fades into a long, cold cloud of icy leftovers. You might expect the first effect to be dramatic, a burst, a visible scar in the sky. Instead, the first effect would likely be bookkeeping, gravity rewriting the paths of distant bodies one by one, more like a hidden hand nudging marbles than a fist smashing glass. Far from the Sun, objects move slowly and hold fragile paths. That means even a passing mass can rearrange them. A black hole entering from the outer dark would tug on icy bodies, bend their orbits, and send some inward on long trips that might take years or centuries to finish. The first danger might be delayed. That delay matters because it breaks our sense of sequence. We expect cause and effect to touch. But in space, the cause can happen in silence, and the effect can arrive generations later. A black hole could disturb the outer reservoir first, and only much later would inner planets feel the rain of consequences. This is why the Loeb and Siraj idea is so useful in our thought experiment. They were interested in flares from small bodies falling toward a planet-mass black hole in the outer solar system. The exact object in our simulation may be different. The lesson is the same. Invisible masses advertise themselves by the trouble they stir up. Now let the intruder come closer. Suppose the black hole is not supermassive. It is not the kind that sits at the center of a galaxy. It is more modest by black hole standards, carrying about the mass of a star, or maybe less. That is still terrifying, but it changes the shape of the terror. Here is the surprise pattern the physics keeps giving us. You expect the black hole to suck everything straight inward. What it actually does first is compete with the sun by adding a new source of gravity. It feels less like a drain opening and more like a new weight dropped onto a stretched sheet. The outer planets would be the first big worlds to notice. Their paths are already wide and slower than those of the inner planets. A new mass passing through that region could tilt those paths, lengthen them, shorten them, or in extreme cases throw a planet outward or inward. The change would be orbital before it became visible. Picture Neptune missing its usual step by just a little. Picture Uranus carrying that difference forward, year after year. On a kitchen table, it would be like nudging one moving coaster and then watching every coaster around it slowly drift off its old track. Nothing explodes at once. The pattern breaks first. Then the effect starts moving inward. Jupiter matters here more than almost any other planet, because Jupiter is already the solar system's great traffic officer. It bends comets. It protects and redirects. If a black hole enters a region where Jupiter can feel it strongly, the whole system starts sounding less like a solo and more like two drummers fighting over the beat. In one version of the simulation, the black hole passes well above the flat plane where most planets travel. That sounds safer, and compared with a direct plunge, it is. But even then, gravity does not need a collision to change a future. A flyby can leave the solar system alive and still leave it permanently different. In another version, the path is worse. The black hole comes through the planetary plane. Now each near pass matters more. Each angle matters more. A small change in direction at millions of kilometers can become a giant change years later because orbits remember. At this stage, people often ask whether Earth would be swallowed. The honest answer is that swallowing is only one of several bad outcomes, and not the most likely in many paths. Ejection is possible. Orbital distortion is possible. A colder, dimmer, unstable future is possible. The drama is not always a fall inward. Sometimes it is being thrown away. NASA gives us the clearest anchor for understanding this. If you replace the Sun with a black hole of the same mass, the planets would stay in their orbits. The solar system would get much colder, but the orbital geometry would not instantly fail. That one fact destroys the old movie logic in a single blow. You expect the black hole to grab the planets just because it is a black hole. What actually matters is that the Sun's mass would still be there, only compressed. It feels almost impossible at first, like hearing that a tiger in a locked box can cast the same shadow. But gravity cares about the weight, not the name. Now, our simulation is not literally replacing the Sun in a clean swap. A real intruding black hole would arrive with motion, angle, and timing. That makes the situation messier than NASA's simple comparison. But the comparison teaches the core rule. Black holes are not special at long range because they are black holes. They are special because of their mass and proximity. So let us keep moving. Months into the approach, then years, astronomers would begin to argue over odd signals. A comet path looks strange. A far object accelerates in a way that seems wrong. A planetary calculation starts needing a correction that no known body can explain. The system does not scream first, it whispers. That is where the 2024 Mars work by Sarah Gellar's team becomes more than a curiosity. Their point was that even a tiny primordial black hole could make Mars wobble in a detectable way. Scale that lesson upward, and you get a haunting possibility. Before the world sees a black hole, science might see a mismatch. You expect telescopes to find the monster in a dramatic picture. Instead, scientists may find it in the leftovers of precision, in numbers that no longer fit. It is like realizing someone entered your house not because you heard the door, but because one chair is half an inch out of place. The universe often announces itself that way. Soon after that, the inner solar system becomes the focus. If the black hole's path ever brings it near Earth's neighborhood, even a smaller primordial object could matter. That was the point of the CLES team's satellite paper. They argued that a black hole with the mass of an asteroid, passing within thousands or hundreds of thousands of kilometers, could shift satellite altitudes by a tiny but detectable amount. That is such an eerie image. Not a crater, not a fireball, a satellite, drifting a little wrong. Your map app would not suddenly shout, "black hole." But the network under the map, the quiet machine web circling Earth, could carry the first sign. Something cosmic would enter ordinary life through navigation, timing, and measurement. The edge of the galaxy could touch the glass in your hand. Ben Lehman of MIT, one of the researchers on the planetary method, pointed out why black holes would stand out from ordinary interlopers. A black hole transit would likely come from outside the solar system and move at around 200 kilometers per second. That is fast. Faster than the kind of space rock we normally watch. So the simulation sharpens. The object is dark. The speed is strange. The disturbances do not match the usual suspects. Now scientists have a pattern instead of a rumor. And then we reach the human part that makes this feel real. Not everyone agrees on how easy such a detection would be. Andreas Burkert of Ludwig Maximilian University Munich argued that the satellite method could be especially hard in practice, and that a black hole close enough to Earth to detect that way might be extremely rare. This matters because real science is not a choir singing one note. It is a room full of careful doubt. That hesitation makes the story stronger, not weaker. When experts disagree about what is realistic, it means the argument is touching reality instead of fantasy. It means the unknown is still unknown. And that is exactly the kind of space where a simulation is useful, because it lets us test consequences even when the sky has not yet given us a case. Now push the intruder deeper. If a stellar mass black hole enters the region near Mars, Earth, and Venus, the old solar system stops being a clock and starts becoming a negotiation. Every planet is still moving fast. Every orbit still carries momentum. But the balanced center that organized those paths is no longer acting alone. You expect a clean line from here to disaster. What you get instead is branching chaos. In one branch, Earth's orbit stretches and swings wider, changing the amount of sunlight it receives over time. In another, Earth gets nudged inward or outward. In another, Earth survives the first pass, but inherits a future full of unstable close calls. This is where the fear comes back, and this time it has earned its place. Because once the black hole is close enough, the solar system can become dynamically unstable. That phrase sounds dry. It means worlds that used to know where to go no longer do. Jupiter could magnify the trouble. Saturn could pass it on. Asteroids could be knocked loose. Comets already nudged in the outer dark could begin arriving as delayed aftershocks. The system becomes layered danger, not one single event. And if the path is truly bad, if the black hole passes extremely close to a planet, then the movie version finally catches up with reality. Tides rise in rock as well as water. A world can be heated, stretched, or torn. The closer the pass, the less the black hole acts like a distant weight, and the more it acts like a blade. Still, even here, sequence matters. The black hole does not simply switch on doom everywhere at once. It changes one relation after another, sun to planet, planet to moon, planet to asteroid belt, satellite to Earth. The universe falls apart locally before it feels global. And one of the strangest outcomes remains the coldest one. If, by some impossible clean exchange, the sun were replaced by a black hole of the same mass, the planets could keep circling as before while the light vanishes. That is not the likely version of an entering black hole. But it is the version that burns the deepest lesson into your head. Orbit is not warmth. Gravity is not light. In a child's drawing, the sun does two jobs at once. It holds us. It lights us. In physics, those are different jobs. A black hole can do one and fail the other completely. By now, the reveal is in place. The old belief said one black hole means instant swallowing. The larger truth says the solar system would first be measured, bent, cooled, shaken, scattered, and only sometimes devoured. The danger is more complicated than panic, which also means it is more real. And here is where this stops being about one black hole and begins being about us. If the reveal in this story is right, then the way we think about danger in space has to grow up. The universe does not always threaten us with a bang. Sometimes it threatens us with a drift so small only patience can see it. Share this with the one friend who still pictures black holes as giant drains in space. That send gives both of you a better way to tell the difference between fear and physics. Because what we are really talking about now is not only destruction, we are talking about detection, readiness, and humility. How do you prepare for a thing you may not see directly? How do you notice the future while it is still only a wobble? The answer begins close to home. We already live inside a net of precision. Mars tracking, satellite timing, repeated sky surveys, long records of orbit data. The tools that help us run daily life also help us notice cosmic trouble. That is why the GPS idea lands so hard. Your phone feels domestic. A black hole feels impossibly remote. But both can touch the same chain of measurement. A hidden mass passing Earth could first appear not as a mythic image, but as a timing problem. The same is true in the sky. Loeb and Siraj argued that repeated wide-field surveys could catch brief flares from small bodies disrupted near a planet-mass black hole in the outer solar system. That means the search is not only about seeing darkness, it is about seeing what darkness does to passing debris. Geller's team said future work would involve detailed solar system simulations to hunt for wobbles. That phrase should matter to you. Detailed simulations, not guesses, not vibes. Mathematical rehearsals for events the sky may someday hand us. This is how modern astronomy often works. We do not wait for catastrophe and then start learning. We build the language in advance. We test impossible-seeming cases before they happen. And when a strange signal arrives, we already know which questions to ask first. In practical terms, that changes what a future alert might look like. It might begin as an unexplained orbital perturbation. Then a second dataset confirms it. Then sky surveys look for matching transient flares. Then satellite systems are checked for tiny correlated shifts. A black hole warning might look less like sirens and more like a growing stack of evidence. That stack matters because false alarms are easy to imagine. An asteroid can confuse the picture, data can be noisy, models can be incomplete. Burkert's caution about rarity and realism reminds us that nature does not hand out perfect test cases on demand. So readiness has to include skepticism. Now narrow the focus again. What would this mean for you, not as a species, but as a person? It means the future of cosmic safety may depend on infrastructures you barely notice. Precision clocks, navigation satellites, planetary tracking, survey telescopes scanning the same sky again and again while most of us sleep. That domestic anchor is worth holding. You wake up, you check directions, you trust the time on a screen. Far above you, machines keep their careful dance. In one extreme future, those same machines might be the first to tell us that something dark and massive has touched our neighborhood. As the story moves forward, the numbers sharpen. The outer region in Eroshenko's discussion sat around 300 to 700 astronomical units from the Sun. Loeb and Siraj talked about the edge of the Oort cloud, out to roughly 100,000 astronomical units, as a place where a trapped planet-mass black hole might be tested. Lehman described black hole transits with speeds around 200 kilometers per second. Kless's team looked at passages within thousands to hundreds of thousands of kilometers of Earth for satellite effects. And the dates sharpened too. The satellite study was reported on September 16, 2024, in Physical Review D. The Mars Wobble study followed on September 17, 2024, also in Physical Review D. Nature highlighted the idea on September 17, 2024, with a blunt headline about microscopic black holes visiting the inner solar system once a decade in simulations. That is how recent this line of thinking is. Notice what that means. The old black hole story most people carry around is older than the new evidence. Our fear script was written first. The precision script came later. So of course the public picture still lags behind. In the next few years, what changes most may not be the sky. It may be our ability to read the sky. Better repeat surveys, better orbit models, better cross-checks between planetary data and satellite data, better ways of asking whether an invisible mass has passed through. If a black hole ever truly entered the solar system, the biggest difference between terror and understanding would be time. How early can we know? How well can we model the path? How clearly can we tell whether the likely outcome is a distant perturbation, a bad orbital future, or direct planetary danger? Those answers would shape every decision after. And even if that event never comes, the work is not wasted. The same tools help us understand dark matter ideas, hidden bodies in the outer solar system, and the structure of our own cosmic backyard. Looking for the rarest danger teaches us ordinary truth. That is one of science's strangest gifts. So the implication is bigger than black holes. It is that our civilization is becoming sensitive to tiny changes in reality. We are learning to notice minute drifts in orbits, small mismatches in motion, faint flares in dark regions, and subtle errors in systems we once treated as background. That sensitivity is power, but it also demands maturity. The next weird signal in space may not mean doom. It may mean a new asteroid. It may mean a data error. It may mean a hidden object no larger than a planet. Or, in the most dramatic edge case, it may mean exactly the kind of black hole transit these papers invite us to imagine. We will need steadier minds than fear usually gives us. What should you look for next? Look for stories about unexplained orbital wobbles. Look for new work on Mars tracking, satellite timing, and wide-field sky surveys. Look for debates, not just headlines. When researchers disagree in public, the real science is usually alive. And remember the deepest correction of all. A black hole entering the solar system would not become terrifying only because it is dark. It would become terrifying because our home is a moving balance, and even a small change in that balance can grow over time. That is a much more useful fear. It tells you what to watch. Something will be discovered next. Maybe it will be a new clue in Mars data. Maybe it will be a brief flare in a survey image. Maybe it will be a cleaner limit that tells us where a hidden black hole is not. But tomorrow's sky will not be interpreted with yesterday's simplicity for much longer. That matters because the universe is full of objects we do not see directly. We learn them through influence, through bent light, through shifted paths, through numbers that stop fitting the old model. In that sense, the future of black hole discovery looks less like staring into darkness and more like learning to hear a new instrument enter the song. If one ever came close enough to matter here, the first clue might be absurdly modest. Not a cracked Earth, not a burning sky, a tiny wobble in Mars, a satellite a little off, a cold equation refusing to balance. Save this video and come back the next time a strange object or orbital anomaly hits the news. That quiet habit will help you hear the next story with clearer instincts than panic can give you. So carry one image with you tonight. Not a giant mouth in space, not a screaming planet. Just a dark object moving at roughly 200 kilometers per second through a system that notices it first by the way a few trusted motions go wrong. That is the future echo of this whole simulation. The universe will keep sending us mysteries that arrive as disturbances before they arrive as pictures. And if we keep paying attention, carefully, patiently, together, we will meet even the darkest possibilities with something stronger than fear. We will meet them with understanding.